So now we'll look at a second simple harmonic oscillator, a specific version of it that has its own equation. And ultimately, in any simple harmonic oscillator, what we're really trying to do is to solve for that omega value, that value for the angular frequency, based on the physical properties and the forces as they exist in that particular object. So you'll definitely need to start drawing the picture of the pendulum. And what we've done is to pull the pendulum out, and then at this point we will release the pendulum. The pendulum will swing back and forth between its maximum displacements, which in this case the displacement is following a curved path. So that's a little bit different than in the previous example where the simple harmonic oscillator on the spring just moved back and forth along a linear path. But in this case the displacement is following a curved path. Okay, but it won't cause any problems for us. Now obviously we need to think about the forces that are acting on this object. So we'll start drawing those forces. The most obvious force is the weight, and there is some tension which is pointed in this direction. Now what we're going to do is, obviously one of these two guys needs to be broken up into components so we can start to think about the way the forces are acting, since they don't act in one dimension. We could take the tension and break that up into two parts, but in this case it would be wiser to break up the weight into two parts, and the reason for that is that one of those parts points like this, and if you notice we have a line. In this case this line would represent a transversal that cuts across two parallel lines. So in the case where this points directly down, this is the equilibrium position of the pendulum, and then also pointing directly down would be the weight arrow. These two lines are parallel, cut by a transversal. That means that the angle that we've pulled the pendulum out is the same angle in the weight triangle, in the components of the weight. So we have the angle theta, and this is the hypotenuse. This angle, this is the side which is adjacent. That means that the length of this side is mg cosine theta, and then we have one that points tangential to this circle, and this is mg sine theta. I know that's a little hard to visualize. Probably easier if you think about it in terms of this arrow being taken and slid down here to close off the triangle. Then you get a nice right triangle. You get the hypotenuse, you get the adjacent side, which is going to be using the cosine, and you use the opposite side, which is going to be using the sine. Okay, and that's really enough for us to be able to solve the problem. Now, we really don't need to, I will write the equation for this, but we really don't need to consider the forces that are acting in this direction. So the components, or the coordinates I should say, that we've chosen to use are the radial components and the tangential, which would always be perpendicular to each other, just like x and y, or perpendicular parallel components on the inclined plane. We have the radial components which point along the radius, and then we have the tangential, which are always going to be perpendicular to that. In the case of these two, we really don't need to be concerned because the mass is neither moving up the string nor moving away from the string. So there is not only no acceleration in this direction, there is no motion in this direction. So if you imagine what the net force equation is going to look like for this guy, we would simply end up with T minus mg cosine theta, and that would be equal to 0. So nothing particularly interesting except that the tension is equal to mg cosine theta. At all points, the tension will always be equal to mg cosine theta. Now, in the other direction, this is the tangential direction, this is where all of our acceleration comes from, because if you notice there's only one arrow. And just to make it more clear, remember, we don't look at all three of these arrows at the same time. So we either look at the weight arrow by itself, not broken into components, or we break it into components and then we ignore that original weight arrow. So there is no longer this arrow, there is just the tangential and the radial components. Now this guy has no counterpart on the other side. There's nobody pointing in the opposite direction that would cause him to be reduced or to be canceled out. Normally there is a little bit of friction, but we're going to assume that that friction is pretty negligible. The pendulum bob is very aerodynamic and very small, so there'll be very little influence because of the effects of friction. So in this case, we would say F net equals MA, and that is going to be equal to minus mg sine theta. And I say mg sine theta, negative mg sine theta, because of course if I pull this out to the right, then the force that acts on it and the acceleration is to the left. If I pull the pendulum bob out to the left, then the force that acts on it is always going to be towards the right. That is to say that the net force is always opposite in direction to the acceleration. The net force is always opposite in direction to the acceleration. Well, obviously we get some cancellation, and we get an equation that almost looks like the simple harmonic motion definition, except that it is A, not proportional to a simple property like the displacement, but the sine of the angle that you pull it out. Now that sine is a pretty complicated thing. So that creates a little bit of a problem. So I'm going to pull back from a couple of lectures ago where we talked about when you have motion along a circular path like this, you can actually determine the length of this displacement by using a formula that says that S is equal to R theta. Now remember, this is only good in the case where the angle is measured in radians. Imagine that we made a full circle all the way around. The number of radians would be 2 pi, and this formula would say that S is equal to R times 2 pi, or 2 pi R, the circumference of the circle. We can determine the size or the length of any arc that's smaller than that by essentially setting up this proportion, and in this case, this is a generic equation. Our arc length, the length along the curved path, is represented by the letter x, and R, the radius of the circle's motion, is represented by L, not T. Remember, T is the force, and it has nothing to do with the length of this. It's the length of the string. This is what's determining the radius of the motion of this pendulum bob. So that would be x equal to L theta. So theta then is equal to x divided by L. And what that's going to allow us to do is we'll pull this guy back down and we'll replace the angle theta with this x and L, two linear properties that are measured in terms of their distances instead of measuring the angle in just straight radians. So we have A is equal to minus g sine of x over L. Now this is better because I now have the x part in, but the x is still part of the argument of the sine, and that is still a problem. So at this point we're going to start to talk about something called the small angle approximation, and that is a very interesting thing that occurs when the angle of the oscillations are very small. And what exactly is small? That really varies from textbook to textbook. Generally speaking, under 5 degrees, that definitely would be considered a small angle approximation. But I've seen small angle approximations allowed to go up as big as 10 or even 15 degrees and still be considered a small angle approximation. So what we're going to do is I'm going to use this lower portion down here to discuss the small angle approximation. So what we're going to do is we're going to make a little table, and we're going to look at how the angle compares to the value of the sine of the same angle. And so we're going to start with theta in degrees. We'll look at theta in radians, and we'll look at the sine of theta. And of course the sine of theta has no units. Just to remind you, radians are not technically considered to be a unit anyways, because if you notice, the angle is being measured in terms of a distance divided by another distance. These units are going to cancel out. So the measure of an angle in radians is really not technically considered to have any units. Both of these two numbers are going to be numbers which have no units. So let's look at a couple of different angles. We'll do 1, 2, 5, 10, and 20. And you should definitely have your calculator out right now and make sure to go through these calculations and make sure that you can make the same calculations so that you actually will see for yourself and prove to yourself that the small angle approximation actually is a very reasonable simplification that we're going to use for the pendulum as an oscillator. So first of all, let's talk about how do you go from degrees to radians. Well, what you need to do is to set up a simple proportion. That proportion would look something like this. So if we took 1 divided by 360, that would be the same as my missing angle that I'm looking for divided by 2 pi. So 1 degree is to 360 degrees, the same way as this missing angle that I'm looking for is to 2 pi. I'm not going to do any of the multiplication. I just want to set up an equation that's going to allow me to go through quickly and do all of these calculations one after the other. So first I would cross multiply. And then lastly I would divide. So I get 1 times 2 pi divided by 360. So this is going to allow me to turn all of these numbers into radian numbers. So let's go through this very quickly. So first of all, we have 1 times 2 pi divided by 360. Sorry. And that's 0.017453. We're going to plug in 2 times 2 times pi divided by 360. That's 0.034907. Then we have 5 times 2 pi. That's 0.087266. All I'm doing is I'm just changing this number. So the original number was 1, and then to figure out any other angle, I just need to swap this out for 2, for 5. Now we'll do 10. Obviously 10 would just move this decimal over, 0.17453. And 20 would be 10 times more than this one. That's going to move that guy over by 1 decimal place also. Okay, so we have 5 fairly small angles. 1 obviously very small, but even at its biggest 20 degrees, that's still a relatively small angle. So let's plug in our calculator and see what we come up when we take the sine of this angle. One thing to make sure of in your calculator is that you have this in radians, which I have mine in radians, so make sure. This is an unfortunate thing about the curriculum is that this is one area where you have to be in radians. Most of the others we tend to typically stay in degrees. So you'll have to go back and forth potentially during the exam and flip from degrees to radians. You should never make any calculation in your calculator involving an angle or a trig function unless you know for sure that you've got it in the right units. So it just takes 2 seconds for you to flip this into this, check to make sure you've got it in the right mode, and then go ahead and get out of there. And let's take the sine of our first angle, which is 0.17453, and I ended up getting 0.017452. So a change here would be approximately a 1% difference. This place would be 100th of a percent. This would be a 1% change, a 10th of a percent, 100th of a percent, 1,000th of 1% difference. These two numbers are the same to within 1,000th of 1%. Essentially, they're the same. Close enough that we won't have to worry about it. Out to at least 4 significant figures, they give the exact same answer. So let's try the next number. So that's going to be the sine of 0.34907, and that gives me 0.0348999. So again, out to essentially 3 significant figures, I'm getting the exact same answer as I got. The angle is the same as the sine of the angle. But let's continue on. Let's try a little bit bigger angle. So let's try the sine of 5 degrees, which would be 0.087266 radians. So again, out to the 3rd significant figure before we finally see any difference. This is less than a 1% difference. It's about a 1/10 of 1% difference between these two numbers. Just a fraction of 1% difference. Let's continue on to bigger numbers, and in these we will actually start to see a little bit more significant difference between these. But still, first 2 digits exactly the same, and then we see again about a 1/10 of 1% difference between the two numbers. About a 1/10 of 1% difference. Still very, very close, almost identical values. And lastly, we'll do and in this case we're still looking, this is a bigger difference. We're almost up to a 1%. Still less than 1%, about 7/10 of a percent difference between these two numbers. So even at 20 degrees, even at a value of 20 degrees, there's still very, very small difference between the value of the sine of the angle and the angle of itself. And the reason why I wanted to show you this is that it would be easier if instead of having the sine of the angle, we just used the angle itself. And since the two at very small angles give almost the exact same value, we can just replace this. So where we see the sine of theta, we're just going to get rid of that, and we're going to write theta. And that's acceptable as long as we stay at very small angles. And this is referred to as the small angle approximation. So let's take a look at how that's going to change our equation. So if instead of A is equal to minus G sine of x over L, we're just going to replace the sine of x over L with the quantity x over L. Okay, this is the small angle approximation. And that was a crucial thing, because now you can see that I have the displacement of the particle, the pendulum bob, I have the acceleration on the other side, and then I have nothing but constants connecting them. Gravitational acceleration, it was just certainly a constant, and the length of the pendulum's motion is something that's not going to change either. So let's just clean this up a little bit. A is equal to minus G over L times x. Okay, so that's our simple harmonic motion equation. We have the acceleration proportional to but opposite in direction to the displacement, and since the general formula for simple harmonic motion is A equals minus omega squared x, omega squared must be equal to G over L. So omega squared is equal to G over L, and that means that omega must be equal to the square root of G over L. If we think about the period, remember the period is equal to 2 pi over omega. So T would be equal to 2 pi, and then we need to invert omega, so we end up with the square root of L over G. A couple of interesting things to notice about this equation. Number one, just like we saw with the spring, it does not depend on the displacement. So again, it doesn't matter how far you pull this back as long as you stay in small angles, and generally speaking under 10 degrees you have nothing to worry about, but even at 20 degrees the effect is very, very small. There's just a very slight difference between the sine of the angle and the angle. But certainly below 10 degrees, and even better below 5 degrees, there's virtually no difference. The equipment that we have at school would not be good enough to be able to measure this very small difference that you get between these two guys. So the period does not depend on how far you pull it back. That's certainly not an obvious effect. Another interesting effect is it doesn't depend on the mass. If you notice, the mass went out right away in the beginning. That's a little different than the spring. It did depend on the mass. There was a dependence on the mass. But in the case of the pendulum, it doesn't matter what we hang from this thing, whether it's 1/1000th of a gram, a kilogram, or 1,000,000 kilograms, you're still going to end up with the exact same period regardless of whatever you hang from this thing. So let's take just a quick look at an example, and then we'll move on. So if we, for example, have a pendulum which has a length of 1.25 meters and a mass of 0.5 grams, kilograms I should say, and L is 1.25, then we can calculate the angular frequency. Omega is the square root of G over L, so that's the square root of 10 over 1.25, and we end up with omega of 10 divided by 1.25 equals 2.83. Remember, that's inverse seconds. Inverse seconds. And we can calculate the period. Remember, the period is 2 pi over omega. So that means 2 pi divided by 2.83. And we realize you could use this formula. We could go back to L over G. We could plug in the 1.25 over 10, and it'll give us the same answer. So we end up with a period of 2.22 seconds. Before we leave this, obviously, one of the things that you could do is if you measured the period of a pendulum and you know the value of gravity, you could calculate the length of the pendulum. But more interesting is, let me cordon off a little bit of space here, and let's solve for G. If you knew the length of a pendulum and you measured its period, you could use that information to then solve for the value of gravity, and this is a shockingly precise way of measuring the value of gravity, and we'll definitely do this in class. What you would end up with if you solve this for G, of course the first thing you'd want to do is to square everything, and that's going to give you 4 pi squared. The L will stay here on the top. We'll end up with 4 pi squared L. This is after we squared everything over here. We'll move the G over to the other side, and then the T will come down on this side as a quantity squared. So using this formula on any planet, if I just took a string and tied something to it and measured the period of that pendulum and measured the length, I could calculate the value of gravity at the surface of the planet, and it's shockingly precise. Normally it's going to be a very small percent error, probably less than 1% error. Again, I'll always make sure that when I measure this pendulum that I use it at very small angles so that I can take advantage of the small angle approximation.